All right. So previously we have been talking about the in modern pipeline processor we have multiple different kind of hazards, and uh, we have been talking about how to address the structural hazard. In the last lecture, we talked about hey, we can actually guess something, right? So the places where one of the example places that we can guess is whenever there is a branch. But before we talk about branch, again, there is one big misconcept that a lot of people would typically have after they took their first ever computer architecture class is that what's the definition of branch taken, right? So again, I just want to tell you the clear concept regarding branch taken just means that we are changing the direction of program counter instead of going to the instruction that's right next to the current one, we are going to somewhere else. And this somewhere else could be a backward or a forward. What does that mean by backward? It means that we are going back to a memory address that is lower than the current one. What does that mean by forward? We are going forward to a memory address that's higher than the current one. But whenever your program counter, your next program counter is not your next instruction, it's called branch taken. And it doesn't have to be related to your if-else statement or if your loop statement, right? So for example, in this code example that we have shown the last time is that although it seems like when data I not mod 2 not equal to 0, it's a true statement. However, that true statement is actually meaning the case where branch is not taken. So a lot of people, when you answer my question, you keep like ignoring the comments that I'm giving you and keep asking why. And to be honest, if you could pay attention to the hints I gave you, that's actually helpful. And I'm not that kind of professor who would like to put a lot of useless information within a question. In fact, whenever you see the question that I pull up in this class, you should always be aware everything, every condition that I put in a problem is related. I don't put redundant or useless information in a question, to be honest. So even though like sometimes I put comments, again, don't use your own judgment. Based on what the comment says, that would be actually helpful and save a lot of your time, right? So one thing I want to say, right, in if-else statement, a true can mean not taken, right? There is no correlation between true should be taken or not taken when you compile it. It's based on a lot of metrics that the compiler would use to judge, and there is no golden rules on that. And we have introduced two types of branch predictor. The first type of branch predictor we introduced is actually a two-bit local bimodal branch predictor. And there are so many terms here. The 2-bit means that we are maintaining 2-bit counters as the states. And local, it means that those states, they are associated with each branch instruction separately, locally. It's not trained based on other information that's not related to that particular branch. So that's why it's called local branch predictor. So this is the very basic type of branch predictor. However, as it only based on the local branch prediction, there are situations it cannot really well predict. So for example, it's only half prediction accuracy in the branch X. So later in this in the lecture, I talked about another way of making branch prediction, which is using a global predictor. And by global, it means that I don't care. I don't care who generates that branch outcome. I only care the previous histories that generate by all the branches that we have seen. And like this example, I have a 4-bit global history register, meaning that when I make a prediction, I'm only basing on the last 4 outcome of the branch to make a prediction. And when I train the states, it's all based on when I see this outcome, when I see this history the last time, what's the next branch should be. So it's all based on the history, regardless who generates that history. And then I train the states based on what's next, what's going to happen after I see that history. So and this kind of branch predictor is called two-level global predictor. And for this two-level global predictor, in the very beginning, we had a hard time to make it work. And in fact, in the very beginning, its performance is really bad. However, once you get it trained, it can get nearly 100% accuracy when making a branch prediction. And we also had a demo last time regarding, well, since the branch itself, when you have a misprediction, is pretty much reflecting the case where we don't make a prediction. And to make the right prediction or figure out when a prediction gets wrong, you have to resolve all the data dependencies as well as one cycle for the branch itself to figure the right direction. So turns out, if you consider that, the latency of running a branch prediction, of evaluating the cost of a mispredicted branch would tell you how long is it take to execute an instruction, or you can say how deep is your processor pipeline. So based on that, we can pretty much say, well, most modern processors, they have at least 20-ish pipeline stages when you execute an instruction. It also means that each instruction itself from end to end would take more than 20 cycles to execute. And sometimes we see a CPI that's lower than 1. It means that we definitely have a lot more instructions that we will execute concurrently within a processor. So those are the things that you should keep in mind for now. But the quick takeaway and another thing which we later learned is that there's no perfect predictor, right? So why we discussed both later local and global predictor instead of saying that this is better than the other one, because in fact, like these 4 code examples, there's only one you are going to see that global predictor is going to outperform the local predictor. And other cases, they are about the same, right? So there's always a trade-off in hardware design. And there is sometimes there is no clear answer like which one is better. So never try to figure out which one is better, because it's not the right way of thinking about system design or in general engineering question and engineering solution. You always have to make the case, when is this the best, instead of this is always the best, right? So that's one thing you really need to learn as an engineer in computer science. But since we figure out that, okay, there's no best solution if you prefer local or global, how can we design a predictor that works for the general situation? So today we're going to talk about hybrid predictors first. And then once we finish the discussion of the branch prediction, we can talk about data hazard, which is another type of hazard that we have to deal with. So since there is no best predictor in either local or global, then why don't we take the advantage of both to make a hybrid predictor, right? So that's sometimes why we want diversity, right? Because you see different opinions, you see different strands from different people, right? Same thing here. For predictors, we want they have different opinions, they have different inputs, and then they would generate different outcomes. And sometimes this outcome would better fit for different situations, right? So hybrid predictors has this kind of concept. And the first type of hybrid predictor that I'm going to talk about here is called tournament predictor. So tournament predictor is interesting in a way that it combines local predictor and a global predictor. And how does it make a prediction is that on top of either local and global predictor, we have a predictor. We have a predictor. So what's the meaning of predictor? So here again, in this picture, we have a local predictor, which is pretty much the same as your 2-bit local predictor. We also have a global history predictor, which you can consider is pretty much the same as a 2-level global predictor that I introduced. And in a branch target buffer side, now I reintroduce the idea of states. So how am I going to use this whole things together? So this tournament predictor actually has the concept of using predictor to predict which predictor is going to give you a vector prediction. So the concept of tournament predictor is that we use a predictor to predict which predictor will give you a vector prediction. Do I need to add more prediction in a sentence? Okay, so what does that mean is that whenever I see a PC, if I see it as a branch, based on a state that I recorded or I updated associated with that PC, I decide which predictor would give you more accurate result. And I would take the prediction from the predictor that I predicted to use. And the training of this state is based on priori experiences. Right? So for example, okay, whenever you need to make a decision, you have a lot of people to consult. You have your professor to consult, you have your parents to consult, you have your friends to consult. Right? So for example, one of the most difficult decisions that I have to make every time is where to get my dinner. Right? And sometimes I ask, for example, a friend like Alvin, right? Or maybe another friend, Andrew, right? Then the last experience that I would have with Alvin is that, okay, it's really delicious, right? And for Andrew, my feeling is like, what kind of food are you eating every day? Right? Then the next time, if I have this question, where to eat dinner, who are you going to follow? Alvin, right? So pretty much like right now, if I meet a PC and in the very beginning, I would randomly choose one, right? And both would give you a prediction, right? However, the last outcome, it shows local is more convincing. Then the next time, I would go with local instead of global. Of course, here you can have multiple bits so that you can make an either more like you can have your confidence level trend better, right? But here's the concept, right? I have multiple predictors to consult, and based on the prior experience of the confidence in prediction, I make the prediction based on the one that sounds more confident. That's the concept of tournament predictor. Very simple, right? So, so the concept is that whenever you have a PC, I look up the target PC as well as which predictor to trust. And which predictor to trust is basically based on which predictor can make the right precision the last time. And with that, I make a prediction. And in the meantime, I train both predictors to make an accurate prediction, right? So it's a hybrid predictor that both predictors make prediction, but I only take the one with higher confidence, right? So that's the concept of tournament predictor. And the other type of predictor is called TAGE. So the TAGE predictor is actually coming from the fact where if you take a look of our predictor, right? Global predictor in general is a good idea. However, it has the limitation if the history isn't long enough, right? However, there are also cases where the global predictor won't make a good prediction if the history is too long. Because whenever you have a longer history, you are more likely to get noise in some sense, right? So there's no, so again, right, some people would ask, okay, if longer history can help us taking this pattern, why don't we just make like an arbitrarily long prediction? Of course, there are many considerations right there. For example, if you have 100 bits in your prediction, in your history, you need 2 to the 100 entries to train those states, which is a large overhead. You're not going to do that. So hardware overhead is one thing. And the other thing is that even though I can build that, it may not be beneficial because there are too many noises that would affect the prediction. And the other thing is that training so many states is very time consuming. So you might not even have your prediction mature before your program finishes, right? So that means that longer doesn't mean better, but it also means there are cases where we need longer predictor. So what can we do, right? So here we come to the idea of the Tage predictor. So Tage predictor, it has a very long global history register. However, don't get me wrong. So here, it doesn't mean that we are going to use that very long history to make a prediction. Instead, it's still a hybrid predictor in a way that, again, the branch target buffer has the branch PC, has the target PC. However, when we make a prediction, there are several different predictors that we would take into account. One is the base predictor. You can consider this is potentially like a global predictor with very short history, or a local predictor that has each PC trend with their own states. So there's a base predictor, give you some kind of prediction. However, there's also a predictor that translates based on different history lengths. So here, by history length, is that you would have predictors taking different lengths from your history to make a prediction. And whenever we want to make a prediction, we take the ones with the longest history with the highest confidence level. So for example, if now I have a pattern that I can find here and here, but if this one is highly confident, this one is not, then I would take this one instead of this one. So this kind of design would help us to identify the most appropriate length to make a prediction for each different branch. And if I cannot find anything, I can still make a prediction based on the base predictor. Question?
Why is it still a local predictor?
Because there is not always the case where I can find a match in history, and I still need to make a prediction. And it's still better to make a guess or not make a guess, right? And again, there are also cases where the local predictor is going to give you a better outcome, right?
So the base predictor is a local predictor?
Yeah, it could be a local predictor or a global predictor. There is no golden rule for that. It's based on your choice. Okay, so this is the basic design, and inside each table, you would that's based on the paper, right? So you can go into that paper, that you will find exactly the same. They use a 3-bit counter to train the prediction. And so the 3-bit counter, again, is still a saturated counter. And if it's greater or equal than 4, then equal to 4, then we will predict taken, otherwise predict not taken. And there is a partial branch PC, which basically the suffix of your branch target branch PC address as another. You can consider it as some kind of tag. And so whenever I find there's a match between the PC and the tag, I would make a prediction using the history that I have, and then I would trend the usefulness based on that, right? So this is somewhat global, somewhat local in a way that when I trend this history, I can also take a look. I use the global history to train the prediction for each PC, right? So when I train the predictor, it's a combination between local PC and a global history and the prediction, as well as the confidence level, right? So you can hear it takes into account many information, right? The different branch PC, different lengths of history, as well as the previous result, right? So this is what it trains, but this is what it used, right? So it turns out this tech predictor. So for example, if right now I have a PC, and what if I can find a match in multiple predictors, right? And both of them showing that they are useful, right? If that's the case, then I would trust the one with the longest history, right? That's the idea of the tech predictor. And the best predictor is used if there is no match, right? So you can still make a prediction because, as we mentioned, right? Sometimes it's hard to find a match, but better doing something than doing nothing, right? So that's the concept of tech predictor. Another one, which some of the machine learning guys you might be very excited about, is called perceptron. So if you take a look of when a paper is published, it's actually in 2001. So this gives you an evidence that architecture people, we are actually the earliest group of people who try to incorporate machine learning as part of our problem solution, right? So what's the concept of perceptron? So if you think about branch prediction itself, it's essentially a pretty classical machine learning problem in a way that we want to have some kind of stuff learning something to predict the upcoming branch outcome, right? So it's like you want to have a classifier and it gives you the outcome taken, not taken, based on some input information, right? And this information, what we have heard so far, it could be local history, it could be global history, it could be the PC, right? So those are the features that you would extract from your program, right? And so in fact, right, you can also think about the stuff that we have been introducing. There are also some sort of machine learning mechanisms, but they are just not the neural networks that you have been thinking about. It's just a different way of making prediction, right? And since the problem itself is essentially the same, why can't we just apply the concept of neural networks to solve this machine learning problem, right? So that's why people start to think about how can we use perceptron, which is one of the earliest neural networks method back to 25 years ago to make a prediction for our branch, right? So if you want to map the branch prediction to neural networks, as I said, right, your inputs, one of the ways to do it is that your inputs or the features that you extracted from your program is basically the outcome of priori branches, right? And when we talk about the outcome of priori branches, it's upon your personal choice when you want to make a decision of what your predictor design should be, right? It could be local, it could be global, whatever, right? And the output of your perceptron could be formulated into two different classes. And for since this is linear algebra, so for the optimization purpose here, we formulate it as +1 and -1. So you have a separation, and it allows you to do some kind of linear combination in the very beginning, right? But to be honest, this is what we would expect, right? Your outcome is either taken or not taken, which is +1 or -1, right? And you can use a global or local history. It's up to your choice. And later on, you will figure out using global history or local history probably doesn't matter. And it's probably better to use global history for some reason. And so with that, what basically is saying that if I have n-bit history, I use this n-bit history with a set of linear algebra operations, which is basically a set of weights that I could multiply, and that would give me a value in this linear algebra function. And this function would give me an output that's between 0 and 1, and I predict taken or not taken based on its 0 or 1, right? That's the meaning of it, right? And when I run this, in the very beginning, when I train this, and during the process, right, I consistently update my weights, which is a table in my hardware, to see if I adjust the weights in this way would help me generate more accurate result, right? So this kind of story you probably are very familiar with. So here is the hardware organization of the predictor, right? So basically, for example, if you have, if you say, well, I want to make a hash table, and each hash table is associated with a set of different weight vectors, right? So for example, here, saying that I want to have 16 different weight vectors for my predictor to choose, to train, right? And then for the branch PC, for each branch PC, I can mod I can mark it by 16. So you can hash the branch PC into one of the weight vectors, right? So based on different PC, you will have different weight vectors to train, right? So this way, it sounds local, right? This way, it sounds local because I can train the weight vectors separately for each branch PC, right? And then when I want to make a prediction, right, I take the associated weight vector and use my global history register to multiply the weight vectors in this table and to get the prediction result. And when I want to train, it's also the same weight vector that I would update. However, when I make a prediction, I can take the global history register. So in this way, it also has the flavor of global prediction, right? So that's why this is still a hybrid predictor, because when we make a prediction, it's not simply based on the information that's only local to this particular branch. And here's the training algorithm provided in a paper. But based on the algorithm, let's run through an example. So right now, saying that I have a global history like this, right? Taken, not taken, not taken, not taken, 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 not taken, 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 not taken, not taken, right? This is the history that I currently have, right? And based on this history, right, the branch X is likely a taken, right? So then, now, so with that, right, with that, what happened in this algorithm? Okay, if the last time branch X taken when these bits are set to 1, I would give these bits higher confidence level, right? So that's what the algorithm is doing, right? When the last time I saw it's taken, I give these bits higher confidence level, right? And then saying that right now, I see this history, and the branch X is still a taken, right? Then based on this, you will find I keep incrementing the bits that are ones with some weights, right? Then you can see, okay, if this ones, so saying that everyone I incremented by 0.25, for example, right? So this is 0.25, this is 0.25, and others are 0, right? And this is now 0.5, 0.25, 0.25, 0.5, 0.5, 0.5, right? And later on, I have another global history. Branch X is again taken, right? And then based on this history, I again increments the bits that are ones, but decrement the bits that are zeros, right? So you can see some colors, they get lighter or even gone, right? Some colors, they get deeper, right? And gradually, your weight vector can evolve in this way, right? So another way of seeing this kind of predictor as a hybrid predictor is that it helps us to identify the bits in our history that are more relevant to this particular branch, right? So through the way how it trains those weights, those ones with higher weight values, you can also consider the ones that are correlated to the result of the current branches, the current branch, right? And maybe if you go back and look at your code, you will find out, okay, turns out this, they are essentially the current branch, right? And if every time you make a prediction, you only base on the outcome of these branches, then it's a local predictor, essentially. Don't you agree with that? Right? So that's why I'm saying, for the perceptron predictor, it doesn't really matter. You train it, use global or local information. Because, and in fact, you should use global information. Because the training methodology itself would automatically converge to a local prediction through the process when you train the weight vectors. Because if it's unrelated to other branches, it turns out those are zero out. But if they are correlated to other branches, then it would aggregate with higher weights, right? And another thing which you probably will find perceptron really good at is that for those that are noise, perceptron can actually avoid them because you won't give those noise high weights, right? So that's why perceptron actually can make a pretty good prediction, right? So that's the idea of perceptron. And the branch outcomes, the weight vector actually reflect which branch outcomes are more important, right? And sometimes it would end up become the same as local. And sometimes it would be global predictor, but discount some of the noise, right? Which make this predictor a pretty good choice, right? So let's take a look of the branch prediction mechanism that are used in modern processors. And in fact, you will be surprised. All the predictors that I introduced so far has ever been used by some processors. Like, okay, the local predictor sounds useless or the global predictor sounds useless. But in fact, in a processor 20 years ago, like Pentium M, some of you might also have the computer based on these processors. They use those predictors. And for modern processors like AMD Ryzen processors or like a mobile phone processors by Samsung, they all have perceptron-based predictors. So so you will be surprised how eagerly are people to integrate good branch prediction methods into our processors. And the main reason, if we go back and look and see, is that if you don't make a good prediction, whenever you mispredict, it's more expensive than a cache miss, right? So branch prediction is actually a very important problem, right? So, okay, so we can skip this. Now, I have a question for you. Here is the paper describe the predictor used in AMD processor. Can you tell why do they make this particular decision? All right, let's take a look. Okay, of course, we need some discussion, right? So why don't you guys go ahead and discuss with your friend regarding why in real practice they make this decision. Okay. All right, let's take a look. Okay, more of you think the answer is A. Okay, so, one thing that I found interesting, and I found one concept you guys must have when you take a great course is that in the past, when you read papers or you read textbook, you just read through it, you learn how to do it, and you never ask why we need to have this. And you never ask, when should we use this? Right? You only care about what is this. But here, as a grad school, as a grad student, you should start to think the why behind everything. Everything is there for a reason. And everything has its own best place to work out. Right? And when you read papers, you have to compare this paper with another, and sometimes you have to combine multiple papers together. When we select papers, we actually select those papers on purpose for you guys to think about how to compare those. And in fact, a lot of my students, when they enter the job market, they always get questions like a system design question. And to be honest, and they keep asking me, like, how can I prepare for this kind of system design questions? And the answer is that, yes, in a class, we don't teach you leak code answers. However, we teach you system design questions. And this is one of the example system design questions in hardware architecture or microarchitecture in a way, right? So right now, why do we have first level predictor as perceptron and second level as Tage? Why? I actually heard pretty good discussion here. What do you guys think?
We thought that it doesn't make sense for us to put a perceptron, or it doesn't make sense to use Tage and L1 if it's takes a long time. So we think 1 and 2 is false because if it takes too long to train, then it shouldn't be on O1. Like we want a fast, like we want a rough and a fast prediction. And if it's more accurate, then we don't need a L2.
And in fact, okay, let's think about this, right? In terms of the system design, what's the requirement of the L1 predictor? What do we typically want something to be in L1? Fast, right? So what's that tell you? If they pick perceptron as the L1, Tage as the L2, which one is the faster? Perceptron is the faster one, right? So that's why we make that design decision, right? The design decision here is made by, in L1, our requirement is shorter latency. Okay, but for L2, what's the design requirement? Higher accuracy, right? So if you want to have multiple levels of predictors, does it make sense to have a lower accuracy predictor as your second level? No, right? So typically, ideally, why we need both TA and professors? TA is like the first level predictor. If you don't even know the answer, go to the TA, ask TA for help, right? And TA suppose they have more time, right? Professors, because for me, like I'm leading like 4 other students in the meantime, like working on paper revision right now. I have a deadline tomorrow. I have grant to write. And right now the school is adding more and more stuff on us without paying us more, right? Like recently I've been thinking about, should I find a different job, right? But set that aside, right? Like we have longer latency for you to reach out, right? Whenever you send me an email, I cannot respond to you immediately because I actually have, if you want to check, I have thousands of emails that are waiting for me to reply, right? If you get me response in 2 days, it means that you are already my high priority. Trust me, right? Okay, but why do you want a professor? Because suppose the professor should give you more accurate result, or the professor can answer your question whenever the TA is not available too, right? That's why you want a second level predictor. However, it doesn't make sense if you have a second level predictor. It's less accurate than the first level, right? So what does that tell you is the latency of making a prediction, at least perceptron, is shorter. However, perceptron must, here I would say must, not being as accurate as Tage. Otherwise, we could have just used perceptron, right? Do you agree with that? So these are the 2 things that we can conclude for sure, right? So based on that, the first one is not correct. Well, sorry, the first one is something that we cannot tell. There's no evidence here. The second one takes longer to predict than Tage. That's actually false, right? Otherwise, it doesn't make perceptron the first level, right? And the first one, if you say, well, based on what has been discussed so far, you cannot conclude that because there's no evidence showing that it takes longer or shorter to train, right? Okay, perceptron is more accurate than Tage. That's also false. Otherwise, it won't make perceptron won't need Tage as the second level. Okay, so 2 and 3, they are false already, right? So what about the other 2? So first, for L1 and L2, why am I saying that There is no evidence saying that it takes longer to train, because at L1 we just need a predictor to make a prediction, to do something rather than not doing anything, right? So even though the prediction is wrong, that's fine, right? So even though when it's training, it already can make a prediction, right? So there is no evidence regarding its prediction, the time to train. So again, how do we know this? You really have to read a paper, right? That's why you need to read a paper, and you have to compare these two papers together, right? So here are the other things that I gather from both papers, and they both have the results section for you to reference. So in a lot of cases, a lot of people, they say, as an engineer, I don't need to read papers. But again, when you are doing system design, without paying the overhead to really implement something, those papers are your friends, right? So here it tells you which one should I be choosing before I really do something. So this is the figure that I grabbed from both papers, right? So the horizontal axis are log scale hardware overhead. Log scale hardware overhead. So the good thing about log scale is what? You can look at their curve to predict, right? And based on the slope or the gradient, which I think the term you like the best, right? Based on the gradient, right? You can decide which one would go faster, right? So if you look at the gradient on perceptron, how does that look? It's actually flatter, right? So what does that mean? Diminishing returns, right? When you increasing the area, right? So what does that mean? If you have the budget to give perceptron more area, you are actually getting diminishing returns. However, if you look at the Tage, it's not a case. It still scales when you give it more budget, right? So this tells you one thing, right? The fourth statement is actually false, right? Giving the perceptron more, well, we can go back that. But the conclusion is that for perceptron, if you get it more area, it doesn't always help, right? That's the conclusion about perceptron, right? And the other thing, right? If Tage is more accurate, right? You also have to. It also teaches you one thing. In a lot of machine learning problems, people keep thinking neural networks is always the best solution, right? But at least for this one, neural networks is not the best solution, because like mechanisms like Tage works better. In a lot of system-wide optimization problems, in real practice, we find out like simple mechanisms like random forest, they work a lot better than neural networks, right? So if you really want to pay attention and you really want to be an expert in machine learning, using machine learning to solve problems, neural networks is not the only thing you should learn. A lot of classical mechanisms like support vector machines, like random forests, you should learn as well, right? So, but based on that, right, this is an evidence where machine learning doesn't help after a certain degree. Now, the other question, how good is prediction, right? So if you check the prediction accuracy, right, if you compare against both, you will figure out that, okay, I think this is not that helpful. Okay, this is regarding the training rate, right? This is telling you how much time it takes to train a perceptron, right? The horizontal axis is the number of times the branch has been executed. The vertical axis, the time, percentage of mispredictions, right? And based on the paper, it tells you the perceptron predictor is actually is saturated about the same time as the bimodal predictor. right? The two-bit predictor. So what does that mean? It doesn't take longer to train. It doesn't take longer to train, right? So, and if I unmask the stuff that I mask in the paper, right, it actually tells you the L2 predictor has been upgraded from a perceptron to a TEDge, right? They consider using a TEDge as an upgrade, meaning that perceptron is terrible in terms of accuracy, right? And high accuracy per bit of storage capacity. It means that if I give you the same budget, TEDge is doing a better job. If I give you the same budget, TEDge is doing a better job. However, as you can imagine, we have to look over multiple tables at the same time. Multiplexing the read data from multiple tables make the latency longer. So even though it has higher accuracy, in a system design perspective, we want to make a prediction as soon as possible. So we still need an L1 predictor as perceptron. That's why they make such a decision. However, when they make those decisions, don't just accept that. Don't just memorize it. You should try to think about, what does that imply? It tells you perceptron, neural networks, sucks in terms of accuracy, right? Okay, so this question I would say, right, if you look at everything, A, nothing. Nothing is correct. And how do you learn those? Based on the design decision they made, based on the paper you read, right? And if every paper, every design decision, you can review them in this way, that's actually the most important takeaways of taking this class. Right now, you know how to appreciate a system design. And once you start to know once you start to appreciate the decision made in each system design, whenever you are asked a system design question, you know how to answer it, right? Why you use a hash table? Why you use a linked list? They must have a reason, right? Why you use hash table plus a tree, right? There must be a reason, right? If you can explain those reasons, that make you sound a better system architect. Okay, but here's the takeaways, right? Non-predictor is perfect, right? Even perceptron, even TEDge, they all have their shortcomings. So that's why modern processors, we have multiple predictors instead of ones. And we use them either in hierarchical or as a hybrid predictor at the same level, like tournament, right? So that's the thing. So now let's talk about this, like exclusive OR. Why is it making our swap a lot slower? And the last time we talked about data hazard, right? So what is data hazard indeed? So data hazard is the case where a later instruction in a pipeline cannot receive the logically correct value for execution. When I say logically correct, to be honest, if you directly fetch the value from the source register, you can still execute the instruction as long as there is no structural hazard. But you're just not going to get the right outcome you want for your program. So that's why we are saying logically correct. So this is some kind of artificial hazard that's created because of the nature of the program. It's because the program itself has the nature, right? So that's why data hazard is also the one the programmer has the most to do with, right? So, and the reason of data hazard coming from the fact of data dependencies that programmer creates, right? So what does that mean is that the output of an instruction is the input of a later instruction. That means there is a data dependency. And depending on the hardware, Sometimes you may have data hazard. Sometimes you won't have data hazard. When you have to wait to get the right result, then there is a data hazard. If you don't have to wait, you can still get the right result, then there is no data hazard. So based on that, first, how many data dependencies do we have here? All right, let's take a look. Okay, most of you identify it's 2, but why don't you discuss with the 2 with others? Maybe you will find your answers differ. Oops. All right, so let's take a look. Okay, after discussion, of course, but what are the 2 that you guys have in mind? Which one? Which 2? Okay.
Line 4 depends on line 1.
Line 4 depends on line 1 on which register?
EAX.
Okay, what else?
And line 3 depends on line 2 based on EDX.
Right, so there are 2 data dependencies here, right? Okay, so How about this, guys?
Oh.
Oh, it's the same purpose, right? All right, let's take a look. Okay, so I love this figure because it means that we need discussions. Why don't you guys go ahead, discuss with others?
No, I think four depended on. No, I think four depended on two. Is the first. So like two depended on one. It's on two. Four depended on two. The first one is a five and one's a five. So second one should be six dependent on. Okay. So it's one, three. Two to three. Two to three. Two to four. Four was five. Four, five, four, six, three, one.
All right, so after discussion, okay, more of you toward five, right? So what are the five? What are the five? Do you want to give it a shot?
Maybe the second is dependent on the first one.
Okay, on which register?
Yeah.
Okay, this one. What else?
I think the second and the third one.
Okay, on which one?
Yeah.
Okay.
And then I think this was a trick question. I think the fourth one, EAX, is dependent on the second, I believe.
Okay. Right, because this is something annoying as 86, right? The second register serves as both inputs and output. Okay, what else?
And then I think this time it will be the fourth register. Depending on that.
Right. Okay, what else?
And then the last one, the sixth, is dependent on the fourth.
Right. So here we go. Okay, so a few things that you can discover. Why people in the past, they love this? Because at the time that we don't have that many registers in our processor. This is actually pretty good because it help us to save the number of registers that we may be using. So we don't need we don't need a lot of memory accesses. Sorry. We can make things work without using a lot of registers, avoiding putting other stuff outside of registers, right? So that's the good thing about it. However, it's a disaster in the pipeline processor. You see a lot of back-to-back data dependency. And some of them, like the first and the second, is depending on the memory operation, right? And the fourth and the fifth is also depending on the memory operation, right? So that means that you are going to suffer very low latency. And sometimes students might feel annoyed. Why am I always requiring you guys to read the x86 assembly in the very beginning? Because there are a few things simply at a high-level language level you cannot tell. Like this data dependency. From the high-level language perspective, you probably see only two. However, in a real instruction implementation, it actually has 5. Right. So from the high-level perspective, you might think, okay, this has the same amount of data dependencies as the other implementation. But in fact, when it comes to the machine implementation, it has way more. Especially a lot of them are back-to-back. Higher likelihood to incur data hazard. Right. So if you draw the data, the execution as the pipeline. So in this class, I would encourage us to draw pipeline in this way. So the vertical axis here, in each row stands for what's going on in the cycle. And each column stands for who occupies this functional units. So we use this representation for a reason, because later on we are going to see more complex pipelines. So this would help us use the same representation throughout the whole class. So at the first cycle, the instruction 1 is using the fetch stage. So that's why we put 1 in IF here. And the second cycle, we use the instruction 1 goes to instruction decode stage. And here we assume we only have this 4 instruction and assume that we have perfect range prediction. So you can safely consider, okay, once we fetched, it's always able to be decoded. And once we free up that fetch unit, it's always safe to fetch the next instruction. So what really problematic is probably here, right? So for the first instruction, we can, what really problematic is here, right? So if we consistently execute the pipeline in this way, what will happen is that at this stage, instruction 3, it needs to execute. However, what you need is the right EDX value, which only comes right after the second instruction writes back, which is here, right? So what does that mean is that if you try to execute this instruction here, you're not going to get the right result, right? So based on that, how many cycles do we have to stall? Well, I think it's silly. Okay, I will skip this, right? So based on that, right, one thing that we can conclude is for this set of instruction, right? Because instruction 3, we are depending on the result of instruction 2, right? So we cannot have instruction 3 advance to its LU stage. So it has to stall here, right? And other instruction, the earlier instruction, they can proceed until this data hazard is resolved, right? So as we said, we need to wait instruction 2 to finish before we can enjoy your result. right? So for this one with only only two data dependency, we have one data hazard that causes a 5-cycle stall here. So that's the impact of data hazard, right? So stall, again, even for this case, it takes 5 cycles, and we only have 4 instructions. It takes 5 cycles, right? So this is not a very good way of dealing with data hazard. So something that you probably already learned from undergrad architecture is data forwarding. So the idea of data forwarding is that instead of waiting all the result back to the register before we can use it, we forward the result whenever the functional units generate that result. So what does that mean is that we add wires to the functional units that would generate the result to all other functional units as the input, right? So for example, ALU would generate results, so we also create wires from here. And also, if you have complex operations, its result could go anywhere, right? So that's the idea of data forwarding. And again, if this is like an e-course, they would spend a lot of time talking about like how to design the forwarding logic. And here I assume, okay, they have forwarding logic that is done perfectly. You can forward your result whenever the result is ready. Okay, with that, right? Even with data forwarding, what's the best you can do? Just save 1 cycle. All right? So that's definitely not the most useful approach, right? So sometimes I don't understand why people spend a lot of time talking about this, right? So how about this? How about this code examples that we have been seeing? So previously with the other version, we see only 1 data hazard with 5 cycles. How about this one? How many data hazards are we going to see? All right, let's take a look. Okay, so why don't you guys go ahead and verify your answer with others?
Right, but it does say that it's losing more takes 5 seconds. That's what I'm basing on. It takes 5 seconds to compute it, so it's going to wait for that to finish. Yeah, right, that's kind of right. So you're based on just put laziness based on that question. So that's
All right, so let's take a look. So after discussion, okay, more of you think it's D, but also some of you think it's E. So let's check this, right? So first of all, for this kind of question, again, a lot of you try to find if there is a trick to deal with this kind of problem, but unfortunately, no, right? So again, you have to draw the pipeline diagram, and you will find out, okay, even though we have data forwarding, the only case that you would save a cycle, you can only save a cycle, right? So what does that mean? That here we still have to stall for 4 cycles. And then since 2 and 3 has the data dependency, right? So another 4 cycles, right? So for now, you already know it takes at least like 8 cycles in stalls, right? So that's why this code is not outperforming than the other version in the pipeline processor, right? Now, if we consistently going up, right, you will find out for the instruction 3 and 4, we are fine because this EX here only serves for the purpose as input, right? So once it doesn't generate the output for instruction 4. So these two, they can go together. However, this one, it still has a stall, right? And finally, right, we finish, right? So 3 places we would have stalls, right? 4 cycle stalls, right? So what does that mean? A few things that you will learn. More data dependency, higher likelihood to have hazards. The other thing is not every data dependency would lead to data hazards, right? So here we do have the data dependency between instruction 4 and 6, but that doesn't cause the hazard because before that you have to address the issue between 5 and 4, right? So to understand the behavior of data hazards as well as your code, you sometimes really need to have the knowledge about the processor pipeline to figure that out. And that's why code optimization is sometimes difficult because you cannot make assumptions regarding how your pipeline looks like, even though it's the same series of processors, right? But here, as long as at least we know, right? Like this 6 instruction takes 19 cycles, so that's why this piece of code is not outperforming. So stall and data forwarding can both address data hazards to generate the correct code execution result, but not very efficient to a very limited degree. So next week, we are going to talk about a better solution for it. But before we talk about, before you leave the classroom, don't forget, you still have 2 assignments to turn in tonight and reading quiz due next Tuesday before the lecture. Enjoy the rest of your week. I will see you next week.